Good morning, everybody. This is Dr. K Bharathi, Associate Professor of Mathematics, Department of H&S, Legal Krishnareddy Engineering College, Hyderabad. Today, I want to share some of the introduction part of graph theory, which has a vital role in different fields of science and engineering. So basically, graph theory is a branch of mathematics, which deals with the application part of graphical methods. Now, first of all, when we are studying one subject means, we will have some questions in our mind. Why to study this topic, where we have the application part, and where we are applying these graphical methodologies in different fields. So first of all, there are a lot of real-world applications of graph theory. So in a table form, we can represent a function. It can be displayed in a graph like x and y axis. We are representing in the table format. And we can represent by table form in a population growth, monthly climate and electricity sources and all. And some of the real life applications of graph data structures include social graphs, knowledge graphs, and so on. And in the human network also, we have so many application codes here. And in electrical engineering, graph theory is used in designing of circuit connections. In artificial intelligence, coming to the application part, we have shortest path problems, minimized graph theory, and we have. So here, these application parts include network analysis, optimization techniques here, and biology also, we have so many applications. And here, the first of all, the graph theory is discovered by the Swiss mathematician Leonhard Euler, which has developed a theorem on graphs, which is famous and known as 7 bridges of Königsberg problem. So coming to this problem, we have 7 bridges for 4 islands. So the problem is here, we have to cross all the 7 bridges and only once touching each vertex without crossing any bridge over. So that is nothing than if you take the 4 islands as 4 vertices, and we have to cover all the edges. So now these bridges are denoted by edges. Now all 4 vertices we have to cover through an edge with 7 edges. So the problem is here, from starting one land to another land, we have to cover all the vertices and all the edges such that no edge is repeated. And for this, actually, we don't have any solution. And without crossing over the all edges, we can't make it, the path is clear. So this is what Königsberg bridge problem. And coming to the concept of the graph theory. So in that graph theory, the basic terminology is we have vertices and edges. So graph is denoted by Z, where the basically Z contains vertices and edges. Now here in the figure A, we have the graph which contains only one vertex with the degree 0. So this vertex is called isolated vertex. So the basic point here, without edges, there may be a graph, but without vertex, there is no graph. So to represent a graph, vertex should be definitely present without any edge. And here from the graph A, we have represented isolated graph, which consists of only one vertex, which is particularly called isolated vertex. So that is a graph. Now from the figure B, we have a graph, right, with 2 end vertices, V1 and V2, which are joined with the edge E, represented by E. So here, the 2 vertices are connected with the edge E. Now, which is coming to the C graph, here we have 3 vertices, which is closed with 3 edges. 3 vertices with 3 edges. And the last figure, 4 vertices with 4 edges. In that graph, we have so many parts are there, so many types are there, directed, undirected graph, open, closed graph, loop, parallel edges, so many things which are coming to know. So the thing is first undirected and directed graph. So coming to the first graph, there is a graph which is pentagon, right, which is closed. So which contains 5 vertices and 5 edges. And we have not represented any is a direction here. So that is the edge E1 is coming from V1 or towards going V2 or coming from V3 towards going V5. We have not represented. So that is called undirected graph. Whereas in the next graph, here the direction is shown. So the edge E1 is coming from V1 and going to V2. So the direction indicates that the E1 edge is out of V1 coming towards V2. So that is called directed graph. Now, the very application part, the most application part of graph theory is one of the problems is utilities problem. So what is the nature of the problem here? In that problem, we have 3 houses, H1, H2, H3. So for those 3 houses, we have to give 3 facilities, namely water, gas, and electricity. So for the 3 houses, all 3 houses require the 3 facilities, water, gas, and electricity. So the thing is, without we have to provide H1 all the 3 facilities, H2 all the 3 facilities, and H3 all the 3 facilities. The point is here, without crossing edges, is there any possibility to provide each house with the 3 facilities? Now here again I have drawn H1, H2, H3. These the water, gas, electricity. Okay, so these 3 and the remaining 3 houses and facilities I have denoted with vertices, and the giving connection I have given mentioning through edges. So just I have mentioned here the graph that we can provide for the first house water, gas. Suppose and H2 for 2 utilities like gas and electricity. For H3, without any intersection, I have provided only electricity. Suppose if you want to provide H1 electricity without crossing, okay, so outside of the plane also we can draw, right? But coming to the H2, we are unable to provide the electricity bill without crossing over, right? So for H1 also, from outside of the plane, we can give the facility of electricity. From H2 also, from right side, we can give the electricity. But coming to the H3, without any intersection of edge, we are unable to provide the facility of either water or gas. So this is called 3 utilities problem, where it has also no solution. And here also we have networking problem. So already we know that one of the application part is we have network theory. And now here we have some vertices and some edges. So namely we have 4 vertices and 8 edges in this problem. Now here V4 is the vertex which is connected from the left side graph to the right side graph. Now there is a connection between all the vertices point through some edges. So there is a network path between all the vertices to reach from one vertex to another vertex. Suppose if you remove V4 vertex, the thing is if you are removing the vertex means the edges which are incident on that vertex will be also removed. So that there will be no connection from the left hand side part to right hand side part. So that is the network problem, and V4 is the key point here which we can cross across the edges from one vertex to another vertex. Now we have some types of graphs here which are simple graphs, multi-graphs, pseudo-graphs and all. Okay. Now here for the first graph A, which is denoted by A, we have 3 vertices and 3 edges, right? So which is closed, right? Now this is the example of simple graph, means no parallel edges happen, no self loops happen. So this is the example of simple graph. Whereas coming to the B graph, what we have, there is here it is edge with 4 vertices and 5 edges. See, V3 and V4, there exists 2 edges. So these two are called parallel edges. Okay? So this is not simple graph. So a simple graph is what? Without parallel edges and without self loops. That is called simple graph. And here we have 4 vertices with 4 edges, right? So there exists 2 edges between V3 and V4. So it is called parallel edges or multi-edges. So it is called parallel graph or multi-graph. And coming to the third graph, here we have, there is a loop, self loop for V1 vertex. So edge is self loop, V1, V2, V3. And the last one is called pseudograph, a graph which contains parallel edges and self loops. So that is called pseudograph, a graph which contains parallel edges and self loops are called pseudograph. So basically a simple graph which contains no parallel edges and no self loops are called simple graph. And here we have some of the graphs definitions, finite graph and infinite graph. See, until now we have seen some of the graphs which contain some number of vertices and some number of edges. So what is finite graph? A graph which contains a finite number of vertices and finite number of edges is called a finite graph. Simply, a graph which contains infinite number of edges and infinite number of vertices is called infinite graph. Basically, throughout graph theory, we are studying about only finite graphs. Next, we have order and size. So, what is the order? The number of vertices in a graph is called as order, and the number of edges in the graph is called as size. So number of vertices is order, number of edges is size. And the third definition is degree of a vertex. Now, apart from the isolated graph, any graph which contains with some number of vertices and degrees, we have to define the degree of each vertex. Now, what is the degree here? How many edges incident on that vertex is called degree of vertex. So, we're coming from A, it is an isolated vertex, no edges or incident on that vertex. So, degree of that vertex is 0. So, basically, the isolated vertex degree equal to we have 0. And coming to the second graph B, here we have some vertices and some edges. Now, let us take the vertex V1. Now, V1, how many edges are coming out? 2 edges. 2 edges are incident. So, here, no need of directed or indirected graph. Basically, 2 edges on that vertex V1. So, degree of V1 equal to 2. Degree of V2 equal to 2. Because 2 edges incident on that vertex V2. Now, coming to V3, 1, 2, 3. 3 edges are incident on that particular vertex. So, degree of V3 equal to 4. And what is V4? Only 1 edge incident on that vertex 4. So, therefore, D of V4 equal to 1. Next, coming to the graph C, now V1. So, how many edges incident on vertex V1? Now, we are counting the degree of V1. Now, the loop should be counted twice. Loop should be counted twice because one going out and one coming out, right? So, basically, the degree of V1 equal to 4 and degree of V2 equal to 3. Degree of V3 equal to again 3 and degree of V4 equal to 2. Only 2 edges incident on V4. Now, coming to the graph D, it is directed graph because direction has shown here. Now, here overall the point is only degree. So, internally we have what is in degree and out degree. So, coming to the V1 graph, now in degree is 2, right? All edges coming towards V1 only, coming towards to V1. So, in degree is 2. Degree of V1 is 2 in degree. Out degree is we have 0 because according to the direction shown in the figure, no edge is going towards any vertex. So out degree equal to 0. Right. So coming to the vertex V6, 3 edges incident on that vertex. So basically overall degree is 3. But while particularly counting in degree and out degree, so 2 edges from V2 and V5 coming towards V6. So what is that? In degree equal to 2. And the next edge, last edge is V6 to V1, which is going out from V6. So that is called out degree. So overall degree equal to 3. In that internally in degree coming towards the vertex V6 is 2 and going from V6 is 1. So in degree 2, out degree 1. Next, coming to the vertex V2, 2 edges are going towards V1 and V6. So out degree equal to 2, whereas in degree equal to 1. See, there is an edge from V3 coming towards to V2. So out degree equal to 2, in degree equal to 1, overall degree equal to 3. So in that way, we can count all in degrees and out degrees of each vertex. So the very first theorem of graph theory is called handshaking property. The theorem statement is in any graph, the sum of degrees of all vertices is equal to twice number of the edges. Now, this is the statement which is called very first theorem of graph theory, where we are applying in every graph. Now, in any graph, the sum of the degrees of all vertices is equal to twice number of the edges. So here, if you have here any graph, so if an edge is, a vertex is present, now if our edge is coming towards vertex, definitely that it has to coming out of the vertex. So each vertex is incident exactly with the 2 edges. See the previous example here. See here, every vertex is incident with 2 edges. So if V1 is 1, vertex is 1, how many edges are incident on that vertex? 2. So similarly, what if one vertex is there, how many edges are incident on that vertex? Exactly 2 edges. If you take another vertex, okay, to make it as graph, exactly 2 edges will be incident on that vertex. So for one vertex, 2 edges, again for another vertex, 2 edges. So that is what totally if 2 vertex are present, how many edges are present? 4 edges are present. So exactly the number of edges will be exactly twice number of the vertices. This will show the proof. And next for that we have the corollary from that theorem. What is that? In a non-directed graph, the total number of odd degree vertices is even. Now, so we know that graph is a set of with vertices and edges. Now, for a undirected graph, what is totally we are taking degree. We are not considering in degree and out degree because direction is not mentioned there. But for a directed graph, we are particularly taking what is in degree and what is out degree. Now, here they are representing degree of all vertices, total. Okay. So, total degree of all vertices is equal to even number of degree vertices and odd degree vertices. It is the combination of even degree and odd degree, which will represent total degree of vertices. So, according to the handshaking property, what according to left hand side we have? This is twice number of edges. Okay. So, that equal to what? Even. Already, even number of degrees is basically even only because every vertex is counted by twice. Already multiplied by 2 is even, obviously. So here, odd degree vertices. Sub may be odd degree vertices. Okay. So if you take all the right hand side, 2 into E, whatever may be the number of edge, either even or odd, we are since we are multiplying with the 2, that is even only. So even minus even, obviously it is even. Therefore, the total number of odd degree vertices is also even. Now we have some types of graphs. So already we know that uh, there may be a graph without edge, but there is no graph without vertex. The first one I have denoted with only 4 vertices. All each is called isolated vertex. So the graph is formed here with all isolated vertices with no edges. So that is called null graph. A graph without edges is called a null graph. Now each vertex is individually called a isolated vertex. So the graph which is formed with isolated vertices only is called null graph. Okay. Next, complete graph. So complete graph, here the basic formula a complete graph is, if you have taken n vertices, there will be existing n into n minus 2 by 2 edges. So complete graph is generally denoted by kn, where n denotes the number of vertices. So if n equal to 1, so that is k1 only formed with isolated vertex. What is k2? Here, 2 vertices are present in between connecting with one edge, right? So K3. Now here K3 with 3 vertices and 3 edges. And K4, 4 vertices with 6 edges. K5, 5 vertices with 10 edges. So K5 in particular it is called as Kuratowski's first graph with n equal to 5 and e equal to 10 edges. And we can prove the number of edges using the formula n into n minus 1 by 2. Okay, so if you substitute n equal to 5, so that is 5 into 4 by 2, 10 edges. Now, what is the complete graph means? The graph which every vertex is joined with every other vertex in the graph, that is called complete graph. See, K3, the first vertex is connected with remaining 2 vertices, second vertex is connected with the remaining 2 vertices and 3 also. So for K4, now we present the very top vertex V1, it is connected with every other vertex, and K5 also it connected with every other vertex. So for K5, what is the degree of all vertices? 4, because it should be joined with every other vertex. So that is K5, complete graph. Now, coming to the regular graph, what is that? If the every vertex degree is equal, one and the same, that is called as regular graph. Now, from the graph 1, where it is in the form of triangle, now we can observe that the order of each vertex is 2. So that is called 2 regular graph. Now, it is a square rectangle, sorry. It is also every vertex is connected with no, every vertex has the same degree 2. So these are the examples of 2 regular graphs. Next we have the cycle graph. So cycle graph is denoted by n, Cn, and n indicates number of edges and as well as number of edges. Because it is a complete graph, wherever we have stored the point, definitely we have to reach that vertex only, because it is complete graph. So here in the first graph, how many edges? 3 edges with 3 vertices, 4 edges with 4 edges, same. 5 edges with 5 vertices, and last one we have hexagon, 6 vertices with 6 edges. So cycle graph, which is a completed graph denoted by Cn, which contains n vertices with n edges. Now the fifth one is wheel graph. So wheel is just you get in the remember that a wheel. There should be a middle point. So like that, it is denoted by Wn, which starts from n greater than 3. So because for 2 only, we can't make it as complete, right? So W4, now it is n greater than 3. Now in the triangle form 3, definitely the center point should be there, which connects all the remaining points like W5, V5, W6 and W7. Next, N cube. So it is a cube denoted in the 2-dimensional and 3-dimensional space. It is cube graph. Next, the thing is bipartite graph. So in that bipartite graph, we have to part by. So in the name itself, by. So it is 2 parted, partition. So the total vertex should be partitioned into 2 subsets, such that there is no connection between the vertices in the first set as well as the vertices in the second set. Okay. So here V1, V2, V3, V4, I have taken in the first vertex set because there is no joining edge between them. Same, second vertex set contains V6, V7, V8. Observe that there is no connection between the vertices in the second vertex set. And the thing is, there should be definitely an edge between these two vertex sets. Okay. So from V1 to V7, we have an edge. From V2 to V8, we have an edge, right? So the next thing is we have complete bipartite graph, which is denoted by KMN. So here M denotes the number of vertices in the first vertex set, and N denotes the number of vertices in the second vertex. So why? When the bipartite graph is called as complete bipartite graph means, say we have to partition the vertex set into two number of vertex sets such that no relation in the first vertex set and no relation in the second vertex set. But the vertex in first vertex should be joined with every vertex in the second vertex set and vice versa. So here say take the K23 complete bipartite graph, which in the first vertex set we have two vertices and in the second vertex set we have three vertices. And the first vertex in the first vertex set is connected with every other vertex in the second set, same as second vertex set. So K24 and K33. So, okay. So in particular, it is called as second Kuratowski's second graph, where K5, it is called Kuratowski's first graph. K5, Kuratowski's first graph, and here K33, which is particularly called as Kuratowski's second graph, complete bipartite graph. Here it is three vertices with 9 edges. Now we have some types of subgraphs here. So given two subgraphs G and H, we say that H is a subgraph of G such that all vertices and all edges of H are G and each edge is the same endpoint of H as representing in G graph. Now here in the types of subgraphs we have mainly 4 subgraphs are there. One is called proper subgraph, spanning subgraph, edge disjoint subgraph, and vertex disjoint subgraphs. Okay. So what is proper subgraph? Now all vertices and all edges which are as in G should be in the H graph. So that is called the proper subgraph. Now coming to the spanning subgraph, when a subgraph is particularly called spanning subgraph of the given graph. So to see that I have taken the graph G, which consists of some number of vertices and some number of edges. So here, when it is called the spanning subgraph, how many vertices I have taken here? 6 vertices. When it is called spanning subgraph, all 6 vertices should be present in the subgraph. See, edges may be present or absent. Now, the total focus only here, the number of vertices. Here in the given graph G, we have mainly 6 number of vertices are there. Now, these are G1, G2, G3, G4, G5, so on. All different spanning subgraphs of the given graph. Not only 5. So many subgraphs will exist. See, in all the spanning subgraphs, we have 6 number of vertices. Irrespective of the number of edges, all vertices should be present. Now we can draw some other spanning subgraphs also. So basically, now number of vertices should be equal both in graph and spanning subgraph. Now, the third point is here we have edge disjoint subgraph. So edge disjoint. So the number itself, the name itself indicates edge should be not common, disjoint. Okay. So I have taken the graph G here, which contains some number of vertices and some number of edges. For edge disjoint or vertex disjoint subgraphs, we have to take 2 subgraphs, where in that 2 subgraphs, there should be no edge common. So in the edge disjoint subgraph, I have taken 2 subgraphs G1 and G2. See that there is no edge common in between them. Okay, there is no edge common in between them. Where in G1, what are the edges present here? We have E1, E6, E7, E8, right? So here in G2 graph, what are the edges we have present here? We have E2, E3, E4, E5. E5 is between V4 and V5. See that there is no edge common in between G1 and G2. So here G1 and G2 are called edge disjoint subgraphs of given graph G. Next, the point is here vertex disjoint subgraphs. Like here, again, vertex should be not common between the two subgraphs. Now we are taken the G. So I have removed the edge between V4 and V5, right? Is there any common vertex between G1 and G2? No. So these two are called vertex disjoint subgraphs of the given graph. See, removing an edge does not affect the vertex, whereas removing an vertex implies edge also should be removed, which are incident on that particular vertex. Now, these are 4 types of subgraphs here: proper, spanning subgraph, edge disjoint subgraph, and vertex disjoint subgraphs. Next, the thing is we have isomorphic graphs. Now, what is isomorphic graph? To say that the given graph is the obtained graph is isomorphic to the given graph. Now, mainly we have 3 points. The number of vertices should be common, the number of edges should be common, and the adjacency should be present. Okay, na? And now, here, I have taken the graph. Coming to the second point, coming to the first graph, here there exists a graph with 6 vertices and 1, 2, 3, 4, 5, 6, 9 number of edges. 6 vertices with 9 number of edges. And I have representing another graph G2 with the same number of vertices and same number of edges. So whether both are isomorphic or not, we have to satisfy the properties of isomorphic graph. So the very first point is in the G1 graph, we have 6 number of vertices. Say G2 graph also 6 number of vertices. In the G1 graph, we have 9 number of vertices. 1, 2, 3, 4, 5, 6, 7, 8. Same. In the G2 also we have 9 number of vertices. So what is the third point? Adjacency should be preserved. Now, from graph G1, so I have written all the degrees of the all vertices. Now we can say that two vertices are there with a degree 2, 2 vertices are there with a degree 3, and the remaining 2 vertices are of degree 4. But whereas in coming the G2, even though same number of vertices and same number of edges, we have 2 vertices or 3 vertices are with a degree 2 and 3 vertices are with a degree 4. Whereas adjacency of the vertices is not preserved here because there is no vertex with a degree 3 in G2, whereas 2 number of vertices are present in degree 6. So here 6 adjacency is not preserved. Both graphs are not said to be isomorphic. Same. Here, second number, in the second graph, we have some 5 number of vertices with 5 number of edges. Now, I am representing the same graph in the different shape, taking the same number of vertices with the same number of edges. So, in the second graph, 5 vertices with 5 edges, same 5 vertices with 5 edges, where each vertex is degree 2. So, from the graph, we can observe that all vertices are with a degree 2. Therefore, we can say that both are isomorphic to each other.